Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 6, Lesson 5. What we're going to talk about in today's lesson is how we see things in a mirror. So when I look in a mirror, how I see myself. So, here's a little mirror that I can see myself in the mirror. But anyway, I can see myself in the mirror. There we go. Oh, and you can see my classroom. So how we see stuff in the mirror. The stuff that we see in a mirror is often called an image. So the production of that image, how that happens. That's what we're going to talk about today. And we are going to talk both about flat mirrors and about curved mirrors. So here is a curved mirror. You can see the classroom has a slightly different shape when it's reflected in this curved mirror. So we're going to talk about how that happens in multiple videos starting today. But before that starts, let's be a little bit more basic. If this is me, and I'm, a person standing here and I have eyes, how is it that I see something? Sometimes when people think about vision, they think of the vision as coming out from the person. And that's not how vision works. Vision works, light comes from a thing to the person. So the way we draw things that we look at is like this. We draw an object that I wish to see as an arrow. So we don't draw objects as a segment. You will lose points if you draw a segment. Bad. It has to have an arrow on one end. And that allows us to determine if things are right side up or upside down. Because if I just draw a segment, you can't tell if it's right side up or upside down. But if it's an arrow, I can tell. So just be really careful in this chapter to make sure when you draw a thing representing an object that we might be observing, make sure that object has an arrow on it. Now, light will come in from maybe a light bulb or maybe from the sun, but there's light in the room and that light is going to hit this object and reflect off. And it is not going to reflect in a specular way. Remember, we talked about that word in a previous video. It's going to reflect off of this in a diffuse way. So there will be light rays coming off of the object, reflecting off of the object in all these different directions. So light comes in from somewhere, hits the object, and reflects off. And so this shows the light reflecting off of the edge of the object. And then what happens is as that light travels out, the light rays diverge. These two light rays that start off really close together get farther and farther and farther and farther apart. They diverge. And so the observer receives these light rays. And the observer, they or she or he, says, those light rays are getting farther apart. And they or she or he mentally follow them backwards to a location where they converge, where they come together. And that is how the observer determines the location of the object. So objects reflect light rays. As those light rays reflect, they diverge, they get farther apart. The observer, and it all happens, in your brain, you don't have to consciously think about it, but you mentally follow those back to the point where they come together. And that's the location of the object. That's how we see things. So, look around you, wherever you are. If you're, at the library, there might be multiple tables in the room, and you can tell some of the tables are close and some of them are far. How does your brain determine those distances from you to the objects? Your brain is using the idea that the light rays from any object are diverging. Follow that path backwards. The location where they converge is where your brain interprets the location of the object. All right, now that we understand that, we can start to understand how a mirror works to produce an image. See, I'm not going to use this pen because it was, did you see those smears? I don't want that. So I'm going to draw a mirror here. There is my mirror, and I'm going to have an object here. And as always, this object is going to produce a bunch of rays. So here's a ray, here's a ray, here's a ray. Lots and lots of rays. And I'm going to draw arrows to indicate that the light is traveling that way. And then when the light gets to the mirror, we're going to follow the law of reflection. And we talked about the law of reflection in a previous video. To talk about the law of reflection, I need a normal, and then I just follow the law of reflection so that these two angles are congruent. And what I see is that the light rays, which were diverging, continue upon reflection to diverge. These 6 light rays going out to the left are still diverging. Now, what's going to happen if I have my observer over here? That's supposed to be my stick figure. The stick figure is receiving these 6 light rays. These 6 light rays are coming to this person. And this person is going to say, hey, I'm going to mentally follow those back and see where they came from. Now, when we do that, when we follow rays backwards, it's often helpful if we use our straight edge. And you don't have to do this. You can try to do a pretty good job of following the lines backwards. But we're going to say this ray came from here. And this ray came from here. And this ray, and if I did a better job of this, came from, here. And this ray came from here. Now, I did that really sloppily, and these rays don't all meet. But if I draw a bigger dot, that's where they all came from. This one and this one, they all pretty much come from there. Do you notice that I drew my rays on this side with solid lines, and that I drew my rays on this side with dotted lines, solid lines, dotted lines? That's because this is the back side of the mirror. Does the light really go over here? No, this is the back side. The light stays on this side, the front side of the mirror. This is called the front side. It doesn't go over here onto the back, but this person, it seems like the light came from over here. So I draw these dotted lines to indicate there isn't really any light here. It just seems like it came from here. And this is my location of my image. This was my object. But it seems like to this person, I see something over here, which we call an image. So that's very similar to this. When I look in the mirror, it seems like, you can't see the mirror, there we go. But if I put a pen here, oh, look, it seems like you see that pen in the mirror? So this one that I'm touching with my nose is the object. And that one over there that you see in the mirror is the image. So that's what I'm talking about. How is this image formed? Well, the light goes off the object, it reflects, and this person interprets this light as having come from here. So that's how an object produces an image. Now, this picture looks a little messy because I drew so many rays. Now that I see what's supposed to happen, I can redraw this picture with just 2 rays. So there's the mirror, and here's my object, and I can draw 2 rays just going off in any direction I want. I'm going to draw this one horizontal. This ray will reflect right back on itself like that. And then this one, I just have to follow the law of reflection So again, my observer over here says, these two rays are diverging, going apart. I'm going to follow them backwards. And when I follow them backwards, dotted lines on the back, where they seem to have both come from is right here. And so I was drawing the arrow, so I'm going to put the arrow right there. So I've got my object and I have my image. So this is much cleaner and prettier. This is kind of a mess, but it's the same idea as this. So that is how a mirror produces an image. Now, once we have drawn that, I can define some things. We're going to talk a lot in this chapter about this distance, how far the object is from the mirror. It's called object distance, and we use the letter P for that. This, from the mirror to the image, is called the image distance. And we use the letter Q. That's a terrible Q. We use the letter Q to represent image distance. So P and Q, object and image distance. Lots of times people want to talk about, how far is the object from the image? You can talk about that if you want, but we don't have a letter or a name for that. That distance is P plus Q. All right. Let me look at my notes and see what else we want to talk about. We will notice that my image is over here. There isn't really any light here. The light bounces off because there is not light here. We call this a virtual image. Later on, I'm going to show you something called a real image, but this image is virtual because it is at a place where there is not any light. This image is called an upright image because the arrow did not get turned upside down. When I look at this pen in the flat mirror, they're both pointing the same direction. So that's called upright. And even though I drew this bigger than this, the image here is the same size. When you look at yourself in the mirror, you're not any bigger or smaller. So same size image. So every image is always described with 3 adjectives. One indicating whether or not the light is actually there. Virtual means the light is not there. One indicating whether the thing got flipped upside down. Upright is the adjective for right side up. The adjective for upside down is inverted. And then one indicating the size of the image. Sometimes the image is bigger than the object. That's called an enlarged image. Sometimes the image is the same size as the object. That's called a same size image. And sometimes the image is smaller than the object. That's called a reduced image. Now that's been a lot of information. Maybe you've been pressing pause and writing it down. Maybe you want to rewind a little bit and write some of that down. But these 3 adjectives are very important. And this third one has to do with what we call the magnification. A magnification bigger in size than 1 means an enlarged image. A magnification smaller in size than 1 indicates a reduced image. And a magnification equal to 1 is a same size image, relating the size of the image to the size of the object. All right, let's talk about that a little bit more. This magnification, capital M. So what I'm going to do, I'm going to use space up here since I have space up here. Capital M is the magnification, and it's defined as the height of the image divided by the height of the object. So if this is bigger than this, that gives me a number bigger than 1. If this is smaller than this, small over big, it gives me a number smaller than 1. Also, sometimes I told you a right side up thing, I can get an upside down image. Sometimes I get an upside down image. Super weird. Let me see if I can show you that in the screen. I can show you an upside down image for a slightly different kind of mirror. I think this one will do. Yeah. So look at the classroom in the image. You see the classroom there? Actually, let me stop the share for a second. There we go. Can you see the classroom there? Now, this mirror has kind of a bulged out shape. We call that convex. This mirror is pretty close to flat, but it has a little bit bulged in shape. We call that concave. And look, can you see the classroom reflected here? Here. There. Okay, let me use another one. This one is also bulged in. Let's see if you can see it there. There you go. You see the classroom? And do you see that the classroom is upside down? Yeah, that would be an inverted image, an upside down image, because these concave bulged in mirrors can produce an upside down image, but we use the fancy word inverted for that. So, share screen. You want to get back to my piece of paper so you don't see big Dr. Platt. Now you see a little Dr. Platt. And here's my screen again. Okay, so if the magnification is negative, that means we have an inverted image. And if the magnification is positive, that is an upright image. So lots of fun, different possibilities for our magnification. And as you can see, I have lots of fun mirrors here, so we can play with them when we're together in class. That's right, we won't play, we'll be serious. We will experiment with them when we're together in class, because we have to be serious. All right. There we go. Oh, and so I have one more addition to this. Magnification is the height of the image over the height of the object. It also happens to be, we could derive this, but I'm just going to tell it to you right now because we have a bunch more things I want to talk about before we're done today. It's also negative Q over P. Very important. So in this case, Q and P are the same size. So Q and P are the same size. And you're like, oh, but what about the negative? When we have a mirror, it's like we have a number line. And as you know, a number line has an origin where there's a 0. And then on the front side of the mirror, which is the reflecting side of the mirror, all the numbers are positive. 1, 2, 3, 4. And on the back side of the mirror, which is sometimes called the non-reflecting side of the mirror, the numbers are negative. -1, -2, -3, -4, and so on. So what does that imply about P and Q? In this picture, the object distance is 3, and the image distance is -3, because the image is over here on the negative side. And so negative -3 over 3, what is -3 over 3? It's +1, which gives me a positive upright image and a size of 1, same size image. So whenever we have a mirror, whether it's a flat mirror, a concave mirror, or a convex mirror, the front reflecting side has positive numbers, the back non-reflecting side has the negative numbers, and the origin is right there at the surface of the mirror. Okie dokie. So that's all the stuff I wanted to say about a flat mirror and how that flat mirror produces an image. This equation, M equals positive HI over HO equals negative Q over P. This is very, very, very important. This equation is true for flat mirrors. It's true for concave mirrors. It's true for convex mirrors. And even later on in the chapter, it's going to be true for lenses as well. So we're going to use this equation over and over and over again. Make sure you have it written down and boxed. Now we have a little bit of time for me to start talking about curved mirrors. So exciting. So these curved mirrors like this. And I am going to start by talking about this concave mirror that's curved in a little bit here. So I'm going to draw a concave mirror. And I'm going to pretend that it's shaped like a parabola. And if it's shaped like a parabola, it has an axis, because parabolas have axes. What do I call the point where the axis and the parabola meet? You know, that's called the vertex. And you also probably remember from your math class that there's a special place, little f, called the focus. So there is my parabola, my parabolic shaped mirror. And I'm going to place an object here. Here's my object. What's going to happen with that object? It's going to reflect light in lots of directions. And so I'm going to draw this a couple times. Actually, before that, let me show you one more thing. Let me show you the parabola mirror again. Let me show you lots and lots of rays of light. What if I have rays of light that are coming in, and these rays of light are parallel to each other, and they're parallel to the axis? I wonder how they will reflect. Well, it turns out that a rule of parabolas is that when I follow the law of reflection, the rays of light all go through the same point. And that point that they go through, maybe for obvious reasons, is called the focus. Do you see how all these rays of light get sent the same place? We're going to make them all focus on, hence the focus, all focus on the same place. These rays of light are parallel, and they come in and they all reflect through the focus. That is something super cool about parabolas, and that's why we call that point the focus. This distance from the focus to the mirror is called the focal length. And of course, it's a positive number because it's on the reflecting side of the mirror. One super confusing thing we do, we call this location, little f, the focus, and we call this distance, little f, the focal length. That's sad that we use this letter, little f, for two different things. I'm sorry, I didn't choose. But it's a location, and it's the distance from that location to the mirror. Now, that's a mess. So I'm going to draw this again a little bit less messy. I'm only going to draw two rays. I'm going to draw a ray that goes from the object to the mirror. And this is parallel to the axis. So how's it going to reflect? It's going to reflect through the focus. This other ray, I'm going to have go to the mirror through the focus, via the focus, by way of the focus. And maybe you can guess, if parallel turns into through the focus, then through the focus is going to make a ray come out parallel to the axis. And so we're going to draw this ray diagram a lot. And you're going to get very used to saying, maybe you can say it with me, in parallel, out through the focus, in through the focus, out parallel. Please say that 100 times. And you will always remember how to draw this ray diagram. How do we do it? In parallel, out through the focus, in through the focus, out parallel. Say it 1,000 times, you'll never forget. Now, if I have an observer here, here's my stick figure. This person sees these two diverging rays and thinks whoa, they came from here. It seems like the image is right there. Object, image. What do you see about this image? You see that this image is upside down. We're going to call that inverted. So somehow we must get a negative number here. Oh, magnification is negative Q over P. Do you see that Q is a positive number here, the image distance, and P, the image distance, is positive? What's negative positive over positive? It's negative. I have a negative magnification, giving me an upside down image or an inverted image. I also see that I didn't ever draw any rays over here. No dotted lines. These are solid lines. So there really is light here. So I get a real image. And I'm going to show you in class with this concave mirror an example of a real image. And it's going to blow your mind. I promise you're going to love, love, love it. It's going to be very, very, very exciting. I'm checking on time. I don't want our time to be up. It's getting close. All right, so I drew the ray diagram, and so it's going to turn out that just like with this mirror, with this flat mirror, if I change the location of the object, that's going to change the location of the image. Similarly, changing the location of this object will change the location of this image. And we're going to do a lot of playing with that and practicing with that and doing equations with that. But you need an equation for that. So this is called the mirror equation. It's very important. I think the derivation for it is in your book. We don't have time for it today. But it says 1 over P plus 1 over Q equals 1 over F. So this is F, the focal length. This is P, the object distance. And this is Q, the image distance. And those three things, object distance, image distance, and focal length, are related via this equation. And it's called the mirror equation. It's worth memorizing. You're going to use it tens of times, maybe even approaching 100 times as we go through this chapter. All righty. Now, I have just a tiny little final summary thing here. I told you that this mirror is shaped like a parabola, and that's why it has a focus. It turns out that carving out something the shape of a parabola takes a lot of time and effort and energy, and therefore gets expensive. So parabolic mirrors are expensive and therefore harder to find. You know what's a lot cheaper is a spherical shaped mirror. All I have to do is have something on this little arm on a pivot, and carve, 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 and I get something shaped like the inside of a sphere. That is a whole lot cheaper and easier to make. Now, let's see. Let me try to draw a better parabola. Here's maybe a better parabola. And let me draw a circle. Now, circles and parabolas are not the same. But do you see that right here in the center, the circle and the parabola are kind of the same shape? So a lot of the mirrors in the world are truly spherical mirrors, but we pretend that they're parabolic mirrors so we can talk about things like a focus. Now, it turns out that if this were a spherical mirror, like that. Its center would be here. In such a way that, and this is all approximate, but this distance, the focal length, is about half the size of this distance. So I double used F. I'm not going to call this distance C. I'm going to call this distance R for the radius. So when I have a mirror, I'm often going to talk about its focal length, and I'm also going to talk about its radius. And you're like, whoa, parabolas don't have a radius and circles don't have a focus. You can't talk about a thing that has both a focus and a radius, except I'm pretending it's both. So what we want to say is, because of this picture, R equals 2F, or F equals R over 2. It's terrible, but live with it. And so we often have a mirror that is shaped like a sphere. And then so we know its radius. And then we're going to divide that radius by 2 and say, well, it's practically a parabola with focal length half the radius. Now, a spherical mirror is not going to work nearly as well as a parabolic mirror. Parabolic mirrors have this beautiful focus. They reflect everything just perfectly like this. If it's a spherical mirror, so now let's pretend it's a spherical mirror, these rays of light that come in parallel, they get reflected pretty close to all through the same place, but not quite. And that is going to produce a blurry image. It's not going to be super sharp and clear and pretty. It's going to be a little blurry because I used a spherical mirror instead of a parabolic mirror. And that blurriness gets a fancy schmancy name. The blurriness is called spherical aberration. Aberration is a difference from what we were expecting or hoping for. And we don't get the super clear image that we would have gotten from the expensive parabolic mirror because we used a spherical mirror. So if you have blurriness, sometimes that's spherical aberration. And that, my physics enthusiasts, is all I have for you today. I hope you had a wonderful time. I hope you've got a lot of great ray diagrams drawn. And I hope you have all the equations written down, including this very, very important one, the mirror equation. So go out there, practice with mirrors, pay attention to all the images you see being formed, and whatever you do, don't break the laws of physics.